Hello everybody, this is Jeff Janess and welcome to our last of the 5 videos on spatial data types. Next up are pyramids, which are a component of many raster and terrain datasets. In these cases, several versions of the data are created. They're used to view at different scales. This greatly improves the display speed for complex datasets. So for example, a raster image can take a long time to display if there are several million pixels in it. With pyramids, ArcGIS might just show a coarser resolution version of the image at large scales when you're zoomed out, and a finer resolution version at smaller scales. You may have noticed that every once in a while when you want to add a raster to your map, then ArcPro will ask you if you want to build pyramids for it. So all this does is make it draw faster. It doesn't change the data itself. Very important to note here that any analysis you do on the raster is done on the original raster, the full data set. No analysis is done on a pyramid. The pyramids are only for making it draw faster. So create all the pyramids you want. Any analysis you do will still be done on the correct version of the data. Now, just for example, I have a few rasters that are around 12 gigs each, and they each have around 12 billion raster cells. But these huge rasters draw almost instantly in ArcGIS. And that's because ArcMap doesn't draw all 12 billion cells, but it rather examines my map scale and then draws only the coarser resolution pyramid that corresponds with that scale. I can't tell any difference on the screen because my monitor wouldn't have been able to show all 12 billion cells anyway. So if I zoom in, ArcGIS shows a different pyramid level, it shows a different resolution. Looks the same as if I was always looking at the actual raster, but it draws much faster. Raster catalogs are a collection of rasters that are treated as a single object. ArcGIS uses the extent of each separate raster to determine what should be drawn on the map. For example, you might have a collection of hundreds of aerial photographs that cover a region. Now, it's kind of a pain to load all these images up into your map at once because it fills up the contents pane and it really slows down the drawing speed. But if you put all of these images into a raster catalog, then you can simply load the single catalog into your map. ArcGIS will determine which individual rasters to display depending on where you're zoomed in. And if you zoomed out too far, then ArcGIS will just show you the set of rectangles that represent the individual raster extents. Next up are relationship classes, and we will use relationship classes in this class. These relationship classes aren't actually spatial data in themselves, but they're sometimes used to define relationships between datasets and geodatabases. So for example, a water pipe dataset may be a bunch of polylines that might have a point feature class of pumping stations. These may be related to each other because the pumping stations never exist without the associated pipes. Now you can set up a relationship class between these two datasets in such a way that selecting or deleting a particular pipe will also select or delete any associated pumping stations. Now, relationship classes can also be defined between non-spatial datasets like tables or between spatial and non-spatial datasets. So for example, a utility network may include a table that has extensive information on property owners. So you get the name, the address, etc. of everybody who owns property there. Now, you also might have a feature class of electrical distribution lines. So the feature class may have an attribute value for all the property owners, where they may only contain some ID value, and that ID value corresponds with each unique property owner. Well, if you set up a relationship class between the electrical lines and the property owners, then you can access the full set of property owner data directly from the utility network dataset. So you click on this electric line and you get all the information on the property owner. Now, for your information, if you want to create these relationship classes, you need to have the standard or advanced license level of ArcGIS. And by the way, if you don't know what I mean by standard or advanced or basic license, go back and take a look at that first lecture on the introduction to ArcGIS Pro. ArcGIS comes in different levels. As a student, you're using the advanced level. Next data type is what we call a data model, and this is for cases where simple data types are not sufficient to describe the complexity of the system. Now, early on, we discussed a feature class. Now, that was the most basic and most common type of vector data set, but sometimes things were too complex for a single feature class, so we made a feature data set we could combine multiple feature classes in. Well, this data model takes that to another level. So this is when even a feature data set is not sufficient. So many industries or fields of study, you get things that are just a lot more complex than just simple points, lines, polygons, or surfaces. All aspects of the data may be intimately related to other aspects. So a river, for example, is generally represented by a polyline feature, but it's much more than just a line. People who manage or study these river systems must consider such things as the hydrologic network, the catchment area, any surface or subsurface flow rates and direction. You got your river order, you got soil characteristics, topography, and even how rivers cross barriers such as roads and dams. Ideally, people who work with rivers would use a sophisticated data type that captures all these characteristics rather than just relying on simple polylines. So in response to this need, Esri and others have developed a number of these things called data models, which attempt to model data in as sophisticated a system of related objects and functions as possible. Many of these are really complex. For example, there's something called the ArcHydro data model, which attempts to capture the complexities of a river system like I just described. Another data model useful to fisheries managers might be this thing called ArcMarine, which models ocean systems using several three-dimensional vector and raster data types, and even includes a number of temporal data types to model how phenomena change over time. If you're curious, here's an example of a data model. This is ArcMarine. Notice it has a featured data set at the top of marine features composed of a whole bunch of separate point and polyline and polygon feature classes. Have another featured data set of these mesh things which sort of define the matrix within which all the other features exist within. Then you have a whole bunch of additional tables and relationship classes that connect them all up. This illustration of ArcMarine is also sitting in your lab exercise and lecture notes document if you'd like to see it. But in general, data models are similar in concept to feature data sets in that they utilize multiple data types to describe complex systems. They're orders of magnitude more sophisticated, though, in the types of data and relationships they incorporate. They're always stored in geodatabases. Data models often include multiple related feature classes, feature data sets, network relationship classes, vector and raster surfaces, and customized tool sets designed to work specifically with that data model. Advanced data models, such as ArcHydro and the ArcMarine I've just been showing you, these even have user communities, case studies, and publications describing them. Next up, the Mosaic data set. This is an example of a data model designed to deliver multiple raster data sets as a single unit. Each raster can have different extents and resolutions, and the data model includes vector data sets that represent raster footprints and boundaries. You can analyze the entire set of rasters included in the Mosaic raster the same way you can any single raster data set. In this illustration, you see all these footprints, but you can turn the footprints and boundaries on and off if you want, so you only see the imagery. There's actually a little bit of confusing terminology here. This thing that we're looking at is the Mosaic data set. Once you start playing with the tools in ArcGIS, you might find that there's something called a tool that will create mosaics. The tool is called Mosaic. It mosaics rasters. The fun part here is that the Mosaic tool does not create a mosaic data set. The Mosaic tool takes several rasters, combines them into a single raster, and gives you a new raster. This Mosaic data set is something different and something much more complicated. It's got several rasters that are used to make it, but each raster still exists on its own. It's still out there and unmolested by the tool. All right, moving on. The voxels. This is a new thing. By analogy, we discussed rasters. Rasters are made up of pixels. These pixels are little squares or rectangles on the ground. A voxel is the same as a pixel, but with volume. So a voxel data set is a data set that describes a three-dimensional region, and it's broken up into these little like Legos or what was that Minecraft game, I guess. So the landscape is divided up into regular size volumes called voxels. Now this data set's kind of fun. As computers have become more powerful, more and more people have become interested in generating these 3D models of objects or of the landscape. They call these things digital twins, and these examples I'm showing here are what we call 3D meshes created from many overlapping drone images, and they're stitched together in a software package called Drone to Map. You can also make these kinds of data sets from LiDAR point clouds, but yeah, you really need that drone imagery to make a photorealistic model. I don't know if any of you ever played with those old ViewMaster toys when you were a kid. You know, you put that little carousel of pictures in there, you look through there, it looks like a 3D image. These software packages are using that same concept, same way your brain can make this 3D image from two photographs. Well, these software packages take these overlapping images and actually construct this really sophisticated 3D model from all those overlapping images. It's really pretty amazing. And that is what I have to say about these special cases of spatial data types. I do want to briefly mention a couple of things about catalog, though. As we've mentioned before, catalog really is the best way to move around data, to copy it, to delete it. If you're going to try and do that out of Windows File Explorer, you're almost certainly going to mess things up or corrupt things. It's tricky to work with spatial data, and catalog is the thing to use for it. However, GIS doesn't always know it when you have done stuff to a workspace. If, for example, you've copied something into a folder using Windows File Explorer, catalog may not know it. It doesn't keep a live view to the workspace. In fact, even in ArcGIS Pro, if you create data or copy data into a workspace, surprisingly, the catalog window doesn't always know it. And so you have to refresh it. Once you refresh it, then Pro takes a clean, fresh look at the workspace and will repopulate the window with all the correct data in there. But you just have to remember to refresh it. Now, you can refresh it using the F5 key, or you can right-click on a folder. Either of those gives you the option to refresh. One last thing, your class handout has an appendix showing the symbols that ArcCatalog uses for different types of data sets, if you're curious. So take a look. These are how ArcCatalog will illustrate a folder, or these non-relational or relational geodatabases, Excel files, feature classes, etc. Right now, one last topic that's really important, metadata. Metadata are data that describe your data. They include things like who created it, the purpose and description it was created for, the dates it might be valid for, and spatial coordinate systems. The best metadata will tell you what attribute fields mean. This is a big one, by the way. If you haven't already, you will encounter a time when somebody gives you a shapefile or something. It looks like it has just the perfect data you want. But you look in the attribute field, the attribute data, and maybe it's, for example, spring flow characteristics. Maybe you want to know how much water a spring is producing. So you get this feature class of springs, and they have a bunch of attribute fields. And one of those attribute fields looks like it has flow data, but the attribute field might be named with some really obscure code, 8 characters that look like just a bunch of random letters, and you just are not sure. And so in this case, you're really hoping that the metadata will define that attribute field, and even better, it'll tell you what units it's in. Are these cubic feet per second, or are these liters per second, or cubic feet per minute? You really, really hope that this is in the metadata. Another thing, maybe you want to map or analyze stand data. You got mixed conifer here, ponderosa pine here, pinyon juniper over here. You want to analyze that. So you get this stand map, and it looks perfect. It has all these veg types across the landscape. Well, what if the feature class you got describes the veg types back in the 1920s? You don't know that unless it's written into the metadata. Maybe this is a historic data set. So if it's from the 1920s, it might not suit what you want to do with it now. So metadata will tell you this. You you pray that it's there. Metadata can also include processing history, and this can be really critical. You might get a raster data set of slope values. Well, all you have is a bunch of slope numbers. Are these slopes in percent slope, or are they in degrees? That information is often not part of the raster data set in any easy way, but it might be in the metadata. The metadata might list the parameters by which the slope data was calculated from the original DEM. And in this case, it will tell you that it was created as percent or as degrees. This can be really, really important. Now, there's hundreds of potential attributes that are stored in metadata. So there's a lot there. Here's an example. This is what metadata will look like when you look at it in ArcGIS. See all this cool information. It is really, really important. It tells you whether the data is valid. It gives you documentation to back up any conclusions you make from the data. You know, if you're doing an analysis on veg type, and from your analysis somebody is determining that they can harvest this area, well, the metadata will give them the documentation to support that management decision. Now, not all data sets have metadata, and this is a big issue. If you make a data set yourself, and you will, if you distribute it to the public, and the public is going to be relying on it, then you should add metadata to it. You should describe what it was used for, when it was created, and how much they should be able to rely on it. Conversely, if you're just making data sets for yourself and they're part of a larger analysis, and you already know all this information, then you probably are not going to spend a lot of time with metadata. It does take time and effort to make. So if it's just for yourself, you'll probably skip it. I usually skip it for the work I do. But if I'm producing a data set for a client, then I am definitely spending a lot of time on that metadata. How do you see metadata? Well, you get to metadata in the little catalog view, but you can reach that view either within the catalog itself, or you can just right-click on a layer in your map and go down to View Metadata. Either one will pop that metadata open for you. Now, here's an important factor. Metadata can be shown to you in different styles. So different industries, everybody cares about metadata. They usually all care about the same metadata elements, but they like it presented in different ways. So a different industry would prefer their metadata be displayed to them in a way that's typical for their industry. ArcGIS helps you out with this by providing a whole variety of different metadata styles you can choose from. These different styles are preferred by different industries or users. The way you get to it, you click the little project tab, you run down to the options menu, then you open up the options window, go to the metadata section, and there are all the metadata styles you can choose from. Something you ought to be aware of. The first time you run ArcPro after you install it, the default metadata style is this thing called item description. Interesting choice, because of all of these choices, item description is by far the least useful. I've found that it's a good strategy to, as soon as possible, go change your metadata style to any of the others. They all are good except for item description. Now, it's easy to edit metadata. Within the catalog view or within the map, you just right-click on the data set you want to edit. Go to Edit Metadata. Pops open the little metadata editor window. Here you can type in any metadata you'd like. We have a whole variety of things here on the left. Notice if you click on any of these, it opens up a whole new section over here on the right. Got your details, your extents. All of this is editable. All of this is available to you. A whole variety of things to work with. Once you've made all the edits you want to do, come up here and click the Save button. That will save your edits, and then you can come back here. We can actually look at our metadata again here if we just right-click here, go to View Metadata. See, it's saved my title. Easy enough to do. Now, here's something fun. Be warned, know about this. When you run an ArcGIS tool, the tool will typically record what you did in the metadata. Sometimes this is great, like I described about the slope. You calculated a slope from a DEM, but you forgot whether you did it in degrees or percent. Well, lucky for you, ArcGIS wrote that into the metadata. But this means that you can often see a record of everything that has ever been done to a particular data set. Again, this is great. This can be really useful. But just be aware it can reveal things that you may not intend to make public. So, for example, when I was gathering data for my class, I asked the Forest Service for some stand data that I could, it's forestry, right? People like to use stand data. So the Forest Service gave me a stand map that they had, and it's in your data set. LeBaron stands. I wanted to use this just to show you examples of metadata. So I opened up the metadata to take a look at what they had done, and boy, they have done hundreds and hundreds of things to the stand data set. And so this is great. But I noticed something that they probably wouldn't want to share with the public. So to me, it looks like at least somebody was having a very bad day when they were working on this, and now the entire world knows it. Now, imagine that you are Forest Service, and you are an employee of the federal government representing that federal government. Is this the type of thing that you would like to share with the general public? So just keep that in mind. Last topic for the day, general data management strategies. It's very common to use multiple workspaces in a single ArcGIS session. This is normal. You do a lot of analysis, you'll probably create tons of intermediate data sets as you work. Thing is, this leads to cluttered workspaces. I mean, it's not uncommon to create hundreds of data sets in the course of a project. This means that you've got a plan about where you're going to keep these hundreds of data sets and whether you even want to save them in the long term. So what I want to sell to you is the idea that you really ought to plan it ahead of time. Before you start the project, plan where you're going to store data. Plan where you're going to store final data sets, intermediate data sets. Create some geodatabases or folders or some type of workspaces where you're going to store them. And then just be disciplined as you work about storing them in the correct places. All right, and that's what I have to say about spatial data types. Thanks so much for listening, and we'll get started on the labs now.